Hi, and this is Lesson 2-1. You're on page 64. We're starting Chapter 2 today. And this first lesson is entitled Using Integers and Rational Numbers. And you'll notice we have plenty of vocabulary to get to, so let's get started with that. The first term you need to get in your notes is a whole number. Now they say here the whole numbers are the numbers 0, 1, 2, 3, and so on. So whole numbers, I always remember them as they are positive numbers and 0 that have no fractional amounts. What I mean by fractional amounts would be a whole number, I'll do this in red, a whole number can't be like 3.2 because that's a decimal or fractional amount. 3 and 2/10. Okay, I can't have fractional endings to whole numbers, all right? Another example would be like 5 and a half. That can't be a whole number because it has a fractional amount at the end of it, all right? Next, an integer. Let's highlight integers. An integer is the numbers like -3, -2, -1, 0, 1, 2, 3, and so on. The dots indicate it goes on from there. So I have a little note. Integers are just like whole numbers, but they can be negative also. So integers also do not have fractional endings to them. An integer could not be a number like 5 and a half. It couldn't be a -3.2 or something like that. It's got to be a whole number, but it could be positive or negative. All right? And you'll notice they talk about positive integers are the ones greater than 0 and negative ones are the ones less than 0. Real quick, when you look at this number line, do you notice every once in a while I see people that they do not put a number line on paper correctly. A number line, 0 is always in the middle. I should maybe kind of highlight that here. And you notice the positive integers are always to the right of 0, and the negative integers are always to the left of 0. When you write a number line, it always sets up that way. The positives are to the right of 0, negatives to the left. Let's stop and practice this. We're going to graph and compare integers. So for example, we have graph -3 and -4 on a number line, then tell which number is greater. So you can see here, they graphed -3 on a number line. I'm going to darken it in. And then they also graphed -4 on a number line. I'll darken that in. And now they want me to compare which is greater. When you look at a number line, the number farther to the right is the greater number. So it's obvious right now, or I hope it is, that -3 is the bigger number. So you notice they wrote -3 is greater than -4. -3 is the larger amount. Let's have you try. I want you to, in your notes, draw a number line, and you can just copy what's up here, and then I want you to graph -1 and -6 and tell me what's greater. Pause the video and do that. All right, so -1 and -6. Here's the plotting for -1. Let's plot -6. Is it clear that -1 is the bigger number because it's farther to the right? Well, that means your statement would be -1 is greater than -6. Let's talk about rational numbers. A rational number is, it says here, integers belong to a set of rational numbers. A rational number is a number A over B, where A and B are integers and B is not equal to 0. Now that sounds complicated. Really, it's not. It says a rational number is a number A over B. So in other words, a rational number is a fraction. Anytime you can write a number as a fraction, it's a rational number. They show you a little picture here, a little Venn diagram of the different types of numbers. Integers and whole numbers are also rational. Integers and whole numbers can be written as fractions. Rational numbers are also in the group of numbers called real numbers. The numbers we work with are called real numbers. I want to make sure that I talk about rational numbers are fractional. Integers and whole numbers can also be written as fractions. And I want to make that clear because previously you heard me say that whole numbers can't have fractional amounts. So, for example, 3.2 is not a whole number because it has this decimal or fractional amount. But I want you to think about the number 3 itself. Couldn't you write 3 as 3 over 1? Just think about that. Isn't 3 over 1 the same thing as 3? Isn't that a fraction? So you notice a whole number can be written as a fraction. So whole numbers are part of the rational number family because they could be written as a fraction. Same thing with integers. So I got to be clear here. Whole numbers can't have fractional endings like 3 and a fifth or 3.2, which is 3 2/10. But whole numbers can be written as a fraction. They just can't have a fractional ending. Okay, when you have decimals, rational numbers would either be terminating or repeating decimals. Okay, so if terminating means it ends, if the decimal ends, then it would be a rational number. If the decimal repeats, it's also a rational number. Okay? The only kind of decimal that would not be rational, and maybe I'll do this in red, would be the following, like pi, 3.1415. It keeps on going with no pattern. That would not be a rational number. We'll talk about those kind of numbers at the end of the chapter. Let me go back real quick. Let's talk about this table. Tell whether, because this is going to be in our homework right here, they're going to ask you to classify numbers. Tell whether each of the following numbers is whole, integer, or rational. Now to do this, I think using that table on the previous page is a great idea. So let's talk about the number 5. The number 5 is definitely a whole number. So I want to go back to the table on the previous page, this little Venn diagram. So 5 is a whole number. I'll put it in here. Does it make sense that if 5 is whole, it's also an integer, rational, and real? It's got to be part of all these because it's inside all of those. So if you go back to the table, do you see how they put 5 is whole? Yep. Is it an integer? Yes. Is it rational? Yes. Okay. Let's look at 0.6 now. Go back to that Venn diagram, that table. Now, 0.6 is not whole because whole numbers can't have fractional amounts at the end, and it isn't an integer for the same reason, but it is rational. Rational numbers can be written as fractions, and 0.6 means 3/5. Does it make sense that if it's part of the rational number group, it would also be a real number? It'd be part of those two groups, but it's not part of these two. Okay? So, going back, that's why in the table, 6/10, it's not whole, it's not an integer, but yes, it is rational. Let's look at -2 2/3. Okay? Same thing. Let me erase what I had before. Now, it's certainly not whole because it has a fractional ending, certainly not an integer, but it is rational. It has a fractional amount in it, and if it's rational, it also means it's real. So this number would be part of both. It would be not whole, not integer, but it would be rational and it would be real. -24. Let's look at that. Now, it can't be whole. Negatives can't be whole numbers, but -24 is definitely an integer. Integers don't have fractional endings, but it could be negative. So if it's an integer, it's definitely rational and it's definitely real. It would be part of all three of these, but it's not whole. So let's go back to my table. It's not whole, but it is an integer and it is rational, it is real. Okay? Let's have you try. Why don't you stop the video? And why don't you try, let's just do a couple. Try number 5 and let's try number 7. Okay, so we're back. Let's quickly label each of these as whole, integer, rational, and then order them. So I'll make a same little table as we did above. I'll put W for whole, I for integer, R for rational. Here's my little table. And let's do the first number. The first number was 4.5. Well, 4.5 is definitely not whole, and it's not an integer because it has that decimal point at the end. But remember, if I go back, it would definitely be in the rational category, which makes it real also. So it's definitely rational, definitely real. Okay? Oops. I need to put a check mark in there. There we go. Did the wrong thing. Let's go to the next number, -3/4. I know -3/4 is not a whole because it's a fractional ending. It certainly can't be an integer for the same reason. But it is a fractional amount. It makes it rational. -2.1. That's -2 1/10. That's definitely not a whole number. It can't be an integer for the same reason. I got that tenth at the end, but it is fractional. It is a rational amount, and it's an ending. It's an ending decimal. And then finally, 0.5. A half. A half certainly is not whole. It's certainly not an integer, but it is a rational number. Now let's order these from least to greatest. So think about a number line. On a number line, -2.1 would be farthest to the left. -3/4 would be next. The positive half would be the next biggest, and 4.5 would be the biggest if I plotted those on a number line. Okay? Let's also we'll quickly do 7. Okay, so same thing. I'm just going to make a little quick table here, and we'll just fill this in. So let's do first 1/6. 1/6 is definitely not whole. It's certainly not an integer, but it is a fraction. It's rational. 1 3/4. It's definitely not whole. It's definitely not an integer because that 3/4 at the end, but it is fractional. 3/4 is a fraction. -2/3. It's definitely not whole. It's definitely not an integer because it's got at the end of 2/3, but it's a fraction. It's rational. And then 0. Now 0 is a whole number. Now remember, if it's a whole number, it's definitely in that integer circle also, and it's definitely, oops, I just mismarked it. It is whole, it is an integer, and that makes it rational. Make sure I got my check marks right. And then writing these in order. -2/3 is the smallest. 0 would be next. 1/6 is a little bigger than 0, and 1.75. If I plotted these on a number line, I'd see that this number's farthest right, that number's farthest left. Ordering rational numbers. They'll give you sample problems in the book or practice problems, and they'll want you to order these things. So when you think about that, so there'll be homework like this, what we want to do here is we just want to make sure that we read the problem. The star's color index is a measure of the temperature of the star. The greater the index, the cooler the star. Order the stars from hottest to coolest. Okay, so we got to keep clear here. The greater the index, the cooler the star. So when we graph these on a number line, this is the smallest number, followed by the -300ths, followed by the 900ths, and the 2100ths is the highest on the line. But what that would mean, remember, the smallest number is actually the hottest star, because the bigger the number, the cooler the star. So when we write these out, we got to understand that the hottest star then is this one. This is the hot star, and the coolest star would be the one that has the biggest amount. Would be here. This is the coolest star. When we order them, you can see that here. Here's the hottest star down to the coolest star. So you got to read the directions carefully. All right, opposites. Two numbers that are the same distance from 0 on a number line but are on opposite sides of 0 are called opposites. Well, here would be a little picture example. The numbers 4 and -4 are opposites. Do you notice how one's positive, one's negative, and they're both 4 away from 0? So 4 and -4 would be the examples of that. You read the expression. When you see a negative sign in front of a variable like this, you want to read that as the opposite of whatever the variable is. So here, it's the opposite of A. So if I wrote this on paper, we don't call that -x. We call that the opposite of x. Oops, opposite of x. Let me write that down. Okay, that's how we should speak that. I know sometimes we all have a bad habit, me included, and sometimes I'll slip out and say negative x. I should not. It should be opposite of x. So, they will have you find the opposite of numbers in the practice homework today. For example, it says here, if a is negative 2.5, then the opposite of a, think about it, if a is negative 2.5, the opposite of a would be positive 2.5, which would be your answer. Or the next one, if a is 3, the opposite of a would be, I misspoke, if a is 3/4, I meant to say, the opposite of a would be negative 3/4. Let's talk about absolute values. The absolute value is a number that represents the distance between a, that number a, and 0 on a number line. This symbol represents the absolute value of that unknown amount. So what that means is the following. Here would be an example of that. If I gave you this on paper, that symbolism shows you the absolute value of 7. So picture 7 here on my number line. This is what this is asking. How far, this symbolism is saying how far is this number from 0? That's what it's asking for. Okay? So let me ask you, how far is 7 away from 0? I hope you're coming up with the answer, it's 7 units away. So the absolute value of 7 would equal 7. This is asking how far are we away from 0. Distance is always a positive. If I asked you how far, what's the absolute value of negative 7? How far is negative 7 away from 0? Well, I hope you're getting the same result. Hey, that's 7 units away from 0. So the absolute value of negative 7 would also equal 7. You can see in this key concept box they kind of address that. If the number you put in the absolute value is a positive, your answer is going to be a positive. If you put a 0 in the absolute value, it's going to be 0. If you put a negative in the absolute value, it's going to work out to a positive also. So absolute values always produce positives unless you put a 0 in there. They have some examples here. You'll have some homework examples and problems like this. If a equals negative 2/3, then the absolute value of negative 2/3 would be, well, positive 2/3. So how far is negative 2/3 away from 0? It's 2/3 units away. Here's a second example. If a is 3.2, the absolute value of 3.2 would be 3.2. 3.2 is 3.2 units away from 0. A conditional statement, that's another vocabulary word, has a hypothesis and a conclusion. If-then statements are the form of a conditional statement. So conditional statements will always be written in an if-then format. The if part is the hypothesis, and the then part is the conclusion. I think a better way of explaining this is just to write a simple example and walk through it. Here's my example of a conditional statement. You notice it's in an if-then format. If you are a freshman at Frankenmuth High School, then you have first lunch. This statement is called a conditional statement. Do you notice it has an if-then format? The hypothesis of the conditional statement, let me circle the word hypothesis. The hypothesis is right here. If you are a freshman at FHS, that's called the hypothesis. The conclusion is the then part of the statement. You can see the conclusion right here. Then you have first lunch. There's the conclusion. It's important to note that if-then statements can be true or false. If the statement's false, if you can show one example where it's false, that would be a counterexample, and it would prove the statement is false. Okay? This conditional statement here, you can see is true. If the statement's false again, if you can give one example where it's false, then that would be, you'd be giving me a counterexample, and you would prove it's false. Here would be a simple example. I'll just speak one. If you wear red, then you support the Frankenmuth Eagles. Think about that. If you wear red, then you support the Frankenmuth Eagles. Well, I'm pretty sure if we talk to a person from Millington, they would say they wear red and they don't support the Frankenmuth Eagles. So that would be a counterexample and would prove my statement is a false statement. If you can show one counterexample, it proves the statement's false. Okay? You will have practice analyzing conditional statements. Okay? Here would be a sample one. Identify the hypothesis and conclusion of the statement. If the number is a rational number, then it's an integer. So I hope you are seeing what I said earlier. Here is my hypothesis right here. That's the if portion of the statement. And here's my conclusion. It's the then portion. Let's see if this is true. Well, remember the diagram earlier on where we had the whole numbers here, the integers here, the rational numbers here, and then outside we had the real numbers. If a number's rational, so if I have a number in this part, does it automatically make it true that it's integer and whole? Well, I hope you're seeing no. If it's here, it's not guaranteed. Like for example, 2/5 would be rational, but it's not an integer or whole number. So this would be a false statement, because I gave an example. Hey, here's a rational number that's not part of the integer group. Okay? In the homework, you're going to have practice with finding opposites and finding absolute values. You can try here. Okay? Maybe try a couple of these. All right. So, let's say we did number 8. The opposite of A should be negative 5.3, but the absolute value of A should be positive 5.3. Let's do one of these. Identify the hypothesis and conclusion. Tell whether the statement's true or false. If it is false, give a counterexample. Here's my hypothesis. Oops. Pen didn't stop. There's my hypothesis. Here's my conclusion. Let's see if this is true. If the number's rational, then it's positive. Well, let me see. I have a number then in this group. Do these numbers have to be positive in this group? Not necessarily. You know, negative 5 would be a rational number. So that's not a true statement. There's an example. Negative 5 would be a number that is rational but not positive. Okay, that was the end of the video. If you have questions, we will discuss it Monday.